All right, same scenario, just more questions. All right, part E, draw a probability histogram and describe the shape of the distribution. So we have made histograms before. This is nothing new or unusual for us, but we've not done a probability histogram. So very similar in terms of what we've done in the past. The probabilities are the parts that go on the vertical axis, and our highest in the table is 0.25. So I'm going to count by fives and go up that high. Okay. Then we need to fill in all of those probabilities. So the first one, a little over 1%, so we're going to go about right here, and we're going to label the middle of the bar. That represents 0 people waiting in line. Now remember, histograms, the bars touch, so then we need 3.5%, so we're going to estimate right about there, 1 person waiting in line. 0.89, we're going to go to about right there. Next one, 0.150, so we're at about 3 people waiting. Then up to 0.25. Ooh, got a little wonky there. 4 people waiting in line. 0.172. 5 people waiting in line. 0.132. 7 and 8 people are the same, so about 6%, 7, 8, and then back to 9 people, 0.035, okay? Your bars should be about the same width, okay? And again, label the middle of each one, and we've got 2 things missing. I hope you know what they are, okay? One is a title, so this is waiting in line at Wendy's. Okay, and then what does the horizontal axis represent? This is a number of people. Okay, and there is another question. Don't forget there's one hiding there. Describe the shape of the distribution. So how would you describe the shape of this? I'm hoping that you say bell-shaped and symmetric. Okay, unimodal and symmetric is another one that you could say, but we're going to start to hear that term bell-shaped a little bit more, but unimodal is fine as well. All right, we're still going. Hang in there with me, gang. All right, compute and interpret the mean of the random variable. Okay, so to find the mean, mu, of the random variable, okay, so you can kind of think of it as the mean of the probability distribution if you want to. I've got the formula here. You find the sum of the x values, okay, those 0, 1, 2, 3, 4, up to 9 customers, times the probability of that many customers waiting in line. Okay, so if you're going to calculate this one by hand, it would be, I'll turn my pen on here, would be mu is, and then 0 people waiting in line with a probability of 0.011 plus 1 person in waiting in line times a probability of 0.035 plus 2 people waiting in line times a probability of 0.089, and you would continue on until you get to all 9 people, or the highest 9 people waiting in line with a probability of 0.035. And if you would add all those together, you would end up with 4.575 people. Okay, now I know that seems a little weird, all right, because you're like, how can you have a fraction of a person? Again, it's an average, and so you can have fractional numbers of people, okay? If you scale that up, you just work out to, you know, that would be like 4,575 people off 1,000 different days or whatever, so don't worry about that. Let me also tell you how to interpret that, okay? So what that means. So this would mean, on average, there will be about, and I'm going to round, 4.6 people waiting in line during lunch. Okay, on average, there'd be about 4.6 people based on all of the information you have. Now, doing this with your calculator actually saves time. As you might imagine, you don't have to type in all of those numbers. So here are your instructions, okay? The X values you put into list 1, okay? The P of X values, the probabilities, you put into list number 2, okay? Then you do a 1 variable statistics, which you should be familiar with, using L1 and L2. So those of you with the prompts, this L2 is what you put in the frequency list part. Those of you without the prompts, you just have to type in the L1 comma L2 exactly as you did before. Okay, and then mu is X bar on your calculator, which we should not be surprised by that. Okay, it's the same as before. That's the mean. Now, when it comes to the standard deviation, I've got the formula there for you, but we're not going to do that by hand. All right, that's a little too much work. But if you look on your calculator and you've already done that calculation that I just showed you, you will find the sigma. Okay, and sigma is 1.95 people. And so let's take the time again to interpret that. Okay, what does that 1.95 people mean? So that would mean that the number of people waiting in line differs from the mean of 4.6 people by about 2 people on average. Okay, by about 2 people on average. Okay, and again, you can say 1.95, that's fine, but that word about kind of covers a multitude of sins, if you will. And then there's one other thing that I do want to point out. It is not necessarily written in your note packet, but if I asked you if we had an unusual event, or how would we determine whether or not it's an unusual event, I want you to think for a second about what you would use. Okay, again, we have the 2 standard deviations away from the mean. We've got the 1.5 interquartile ranges based on percentiles, and we have the probability of less than 5%. Okay, based on the information we have here for F and for G in terms of the mean and the standard deviation, that's how you would determine what is unusual. You would take that mean plus or minus 2 standard deviations, okay? So you take that 4.575 plus and minus 2 times 1.95, and you would end up finding, again with some rounding, that it's unusual to have less than about 0.6 or more than more than 8.6 people waiting in line. Okay, and again, I didn't specifically ask that, but I did want to point it out just so you can start to see the different contexts and how when you have 3 different definitions, if you will, or ways to determine if something is unusual, how you can use the information in front of you to figure out which one is appropriate. All right, thanks for hanging in there with me on that example. I know it was a long one. I would encourage you to try example 3 on your own before starting the next video.